We have discussed about single instance resource allocation graph and how to describe deadlock with single instance resource allocation graph. Next, we shall discuss multi-instance resource allocation graph and how to describe deadlock using it. This is similar to single instance graph. The graph consists of set of vertices and set of edges. Vertices can be processes represented by circles or resources represented by square boxes. And in multi-instance graph, resources can include both single-instance resources and multiple-instance resources. Here we can see R1 and R2 are single-instance resources and R3 is a multiple-instance resource. Each instance is represented by a separate dot within the box representing the resource. The edges can be request edge or assignment edge. The request edge points from the circle representing the process to the box representing the resource. The assignment edge points from the dot representing the instance of the resource to the circle representing the process. So the request edge shows that the process is requesting for the resource and is waiting for the resource. Assignment edge shows that that instance of the resource is already allocated to the process. So here we can see one instance of R3 is allocated to P1 and one instance of R3 is allocated to P2. Now, how to describe the state of deadlock using this graph? Unlike single instance resource allocation graph, analyzing this multi-instance resource allocation graph can be a bit difficult. So we shall try first the matrix and vector method. Here we have three processes P1, P2, P3, three resources R1, R2, R3. Some resources are allocated and some are requested for. So we can use one allocation matrix and request matrix. P1 is allocated with one instance of R3 and is waiting for one instance of R1. P2 is allocated with one instance of R1 and one instance of R3 and is waiting for one instance of R2. P3 is allocated with one instance of R2 and is waiting for one instance of R3. Remaining all entries are zeros. We have only one instance of R1, one instance of R2 and two instances of R3 to the maximum. So all the resources are allocated, hence the available vector is 0, 0, 0. So let's try whether with these available resources we can execute the requests of these three processes in some order. Can we execute P1 now? No. One instance of R1 not available. Can we execute P2? No. Can we execute P3? No. It means we cannot execute any of these three processes. Here each process has made a single request. None of these requests can be satisfied. So all the processes cannot make progress. All the processes will be blocked for an infinite amount of time. So there is definitely a state of deadlock. Now based on it, we shall try analyzing the graph. Here we can see P1 has made a request. That request cannot be satisfied. P2 has made a request. That request cannot be satisfied. P3 has made a request. That request also cannot be satisfied. One instance is allocated to P1 and one instance is allocated to P2. So all the three processes are requesting and all these three requests cannot be satisfied. So there is a state of deadlock. So either by using this method or by analyzing the graph, we can understand a deadlock state from this graph. But from system point of view, how the system can identify a deadlock state with this graph. Here we can see a cycle. Can we use this cycle as an indication of the deadlock state? Here we found a cycle and we found a deadlock state too. So we can try another graph with cycle. Here suppose P2 is requesting for R3, means the instance of R3 is not now allocated to P2. P2 has made a request for R3. So we shall try the matrices and vector method first. Here P2 is requesting for R3. R3 is not allocated, so this becomes 0. P2 is requesting for R3, so this becomes 1. And we have one instance of R3 now available. One instance of R3 is not allocated to any process, so the available vector becomes 0, 0, 1. Now let's try with these available resources. Can we execute all these three processes? Can we execute the requests of these three processes in some order? Can we execute P1? No. Can we execute P2? No. One instance of R2 not available. Can we execute P3? Yes. We can execute P3. And if P3 is allocated, if P3 is executed, then the resource already allocated to P3 will be added to the available resource and the available vector becomes 0, 1, 1. And with these available resources, can we execute any other process? Yes, we can execute P2. And when P2 completed execution, the resource already allocated will be added to the available resource and the available vector becomes 1, 1, 1. And with these available resources, we can execute P1. It means we can execute all the three processes. The processes are not blocked, so there is no deadlock state here. So here we found cycle. Here in the graph we can see cycle. Here we have a cycle and here also we have a cycle. We found cycle in the resource allocation graph and even then there is no deadlock. It means a cycle in multi-instance resource allocation graph is not an indication of the deadlock state. It shows that deadlock may be present or deadlock may not be present. We cannot confirm that a deadlock will be there if a cycle is present in the multi-instance resource allocation graph. So a cycle in multi-instance resource allocation graph is not a sufficient condition for deadlock. But this is a necessary condition because if there is deadlock, the necessary condition circular weight will be present there, and if circular weight is present, a cycle will be present in the graph. So cycle in multi-instance resource allocation graph is a necessary condition for deadlock. If there is deadlock, there will be cycle in the graph. But if there is cycle in the graph, we cannot say that there will be definitely deadlock. It means a cycle in the multi-instance resource allocation graph is not a sufficient condition for deadlock. Deadlock may be present or deadlock may not be present if cycle is present in the multi-instance graph. So to generalize, in single instance resource allocation graph and in multi-instance resource allocation graph, cycle is a necessary condition for deadlock. Means if there is deadlock, there will be cycle in the graph. And in single instance resource allocation graph, cycle is a sufficient condition too. Means if there is cycle in the graph, there will be definitely a deadlock state. But in multi-instance resource allocation graph, cycle is not a sufficient condition for deadlock. Means if there is cycle in the graph, we cannot confirm that there is a deadlock state.